coming along. I am going to rattle through paper 2 this evening as fast as I can. We've got 70 marks. Hey, Sian, thanks for coming. Much appreciated. So I'm going to be... I've got an echo! Right, by the way, that's my other laptop telling me that my webinar is fully functioning, which is excellent. Okay, so I'm going to be going through paper 2 from June 2019. That was the Year 11's paper. I'm going to be rattling through it as quick as I can. I'm going to be doing extension questions on any commonly asked questions from GCSE. I'll try and cover as much as I can. Do be aware, Year 11, that we have not covered organic yet. I am going to do it anyway in the webinar so that you can always go back and watch it. Sian, if I can ask you for a huge favor, if you could just keep tabs on the times in which I do each question. If you go onto a Word document and just do question 1 and note down the time, and when I switch to question 2, note down the time, that would be super useful. Then you can email me over and I'll add it to the webinar so that people just can click on the questions that they want and it'll do that. And it'll take them to it. I can add it as a timeline, whichever it does on YouTube. Okay, right. Let's see if I can share my screen and get this all rolling. Right. I'll go flat. I will also get rid of that and I'll click on that one. You guys should now be able to see my screen. Right. Okay, I'm going to get rid of my keyboard if I can. There we go. Right, we're flat. I'm going to hide that, bring up this. Okay. Did you see our mock paper? I will try, but I may have to leave when my dad comes. Okay, no problem, Sian. Okay, so usual thing, of course, this is June. This is the Year 11 paper. Periodic table is attached. And question number 1. So, as a usual rule, I tend to find that Edexcel seem to have a fairly good routine for their papers. They tend to start off right where they do most of the time, which is on atomic structure. So the diagram shows the particles in an atom of an element, and they're asking us to label them. Fairly straightforward. So, of course, the top one being a proton, and that, of course, since it has a charge. The bottom one, of course, is then your neutron. And your ones going around in their energy levels is your electrons. Okay, I'm going to rattle through. In terms of other questions that tend to come from this particular diagram, they do like you to label the core. So nucleus, of course, in that case. And they do often just say, where do the electrons live? And we're going energy levels. We are avoiding the word shells here. We know that GCSE has moved on quite significantly in the last 10 years or so, and shells has vanished and energy levels is now preferred. The box gives the name of some particles. Use the words to finish off. Use the words, to do the labels. Oh, nice. That makes everything a lot easier. Okay, mass number. Nice to recall, you guys, that you're going to have a definition here. So now they haven't asked you to give a definition. They're just asking you to give the mass number of the atom shown in the diagram. But it is nice just for me to reference saying, make sure you know the definitions. Yeah, this is the total number of protons and neutrons in nucleus of an atom. It's nice to do that. Next, give the mass number of this atom. So, okay, so we're looking at the protons and neutrons in the center and we're ignoring the electrons. So if I just quickly highlight these, 1, 2, 3, 4, 5, 6. So we've got 6 protons. It's nice to be clear on that. 6 protons. And then I've got 1, 2, 3, 4, 5, 6, 7 neutrons. So the mass number there is going to be 13. They would also ask you, of course, who the element is. Now remember that the protons decide who you are. So in this case, we have got 6 protons. So this is going to put us at hydrogen, helium, lithium, beryllium, boron, carbon. So this is carbon based on the fact that it has a proton number of 6, otherwise known as its atomic number. And it's also, because it's 13, this is a rather odd isotope. Isotope carbon-13. Carbon-12 is the most common. Carbon-13 appears 1 every 1,000-ish. So it's relatively rare. Next, complete the sentence about the isotopes. Isotopes are atoms that have the same number of protons. So we know, and I'll give you an example of this now. So if we go for carbon-12 and versus carbon-13, versus carbon-14, we realize that they all have the same atomic number. They have the same number of protons in their nucleus, but they have a different number of neutrons. And just to be aware, to give you those extension questions, it is super common for them to give you an actual example like I have given you. And they would say, using the above element, describe or explain the existence of isotopes. And you would say that all the carbon atoms have 6 protons. All carbon atoms have 6 protons. And then carbon-12 has 6 neutrons. Carbon-13 has 7 neutrons, and carbon-14 has 8 neutrons. So you'd actually have to run the maths on it. That there is the most commonly lost mark. It's often the third one. They will give 1 mark for the same number of protons, but a varying number of neutrons, and then a third mark for the actual numbers of each one of them in it. So a relatively easy start. Okay, next, we then drop into group 7. It's nice to see group 7 making an appearance. So we've got chlorine, bromine, and iodine. Please note that they have ignored fluorine and they have ignored astatine. Astatine, of course, is common. We never tend to deal with astatine. But fluorine gas, by the way, is a pale yellow gas. In fact, it's so pale yellow, it's colorless in reality. Chlorine is a pale green gas. Bromine, right, fill in the blanks. And of course, they've chosen these 3 deliberately, haven't they? Because they all have a varying state symbol. So chlorine, of course, is a gas. Bromine is a liquid. And iodine is a solid. Now, just to explain that to you, because we know that chlorine, of course, is traveling in pairs. Bromine is traveling in pairs. And iodine is traveling in pairs. But the atoms are getting steadily bigger. What that means is we are going to be getting stronger, weak intermolecular forces. So the WIMPs between the molecules are going to be getting stronger. So WIMPs increasing in strength, increase in strength as size goes up. It's nice to make that connection, of course, also to the oils as well. We tend to see, by the way, if anybody doesn't know WIMPs, I kind of invented WIMPs. It just makes remembering and practicing weak intermolecular forces a little bit easier. That's all. So, okay, then we have to give the observation for iodine. And iodine is a gray solid. Now, just to let you know, they don't tend to like you using black. Don't use black. The reason being is astatine would be black if we could actually extract enough of it to actually see it. So we've got to have a difference between the iodine in reality and the astatine predicted. So a gray solid there for iodine. It's nice also to mention that chlorine gas is a pale green gas, but when it's in aqueous, in water, it is a colorless solution, colorless sol. Bromine is an orange solution, and iodine is a brown solution. It's nice then, of course, also to mention the gases, to mention the solids, of course, for chlorine, bromine, liquids, but iodine, of course, so it's a gray solid. It's brown in solution, but it's a purple gas. They do love to talk about the sublimation of iodine, and they use it, of course, in those diffusion questions that you guys will all recognize. Okay, chlorine has 2 isotopes, 35 and 37. I'm going to need a calculator. Oh, no. Spot my... I found it. Found it. Okay, so it's going to ask us to calculate the relative atomic mass. Okay, so we've got 35, chlorine 35, appearing 77.78%. We're going to add that to 37, that's appearing 22.22%. And we're going to divide the whole thing there, giving us 100. Now, it's also nice, of course, to mention that when you get these numbers, chlorine's a great example because you see it more frequently, really, than any others. But in reality, you should be looking at these numbers and you should be going, which one's more common? And you're going, well, that one. So the number that we're going to be getting has to be between 35 and 37, but we're going to be closer to the 35 end. So I'm expecting 35 point something. If it had a 50-50, we'd be exactly 36. Let's run the maths. 35 times 77.78 equals, plus brackets, 37 times 22.22. Close brackets, divided by 100, and I get an answer of 35.4, and we're done. So it's nice, by the way, and also it says also give your answer to 1 decimal place. Lots of students would be would have a habit there of picking up the number of decimal places in the question, but it tells you specifically in that question how much you want to do it to. Next, a student is given an aqueous solution of chlorine water. So that's Cl2 aqueous. Students struggle with equations, so it's nice to talk you through it. Plus a solution of potassium bromide. So there's the formula of potassium bromide, and that's also a solution, so that's aqueous. Right, and right, okay, and it simply says, explain how you can use these 2 solutions to compare the reactivity of chlorine and bromine. Right, so how you can use it to compare the reactivities. Key things there, I'm actually going to highlight those instead. How we can use these 2 and to compare the reactivity. So how are we going to use it? Bullet point number 1, well, I'm going to mix the 2 solutions together. That seems very reasonable. Mix the 2 solutions together. Right, what's going to happen, of course, is that the chlorine has a higher reactivity than the bromine does, so it's going to displace it. I'm going to form KCl and bromine, and don't forget that if you're ever writing down, most common mistakes is that students leave that as BR. Ange, thanks for coming, Ange, great to see you. So most of the time, students very commonly forget the 2s. Do be careful. Any elements ending in "ene" or "gen" in an equation will be in a pair if they're on their own, if they're elemental. So let's balance the equation. Can't remember to do that. Can't not do that as a chemistry teacher. Cool. So we're going to mix the 2 together. What are we going to see? Let's put on our state symbols. That's also going to be aqueous, and that's also going to be aqueous. We're going to form bromine water, and we've already mentioned that already since group 7's appeared. Bromine water, of course, is orange in solution. So I'm going to mix the 2 together, and what I'm going to see is the solution. Chemistry has all the solutions. The solution will turn orange, not brown. It's going to turn orange. Bromine water is orange. So what does that tell us about the reactivity? Well, okay, for the first thing I want to say is that the chlorine is displacing the bromine. Right, and that tells us that the reactivity of Cl is higher than Br. Cool. And by the way, guys, give good bullet points. Don't get me wrong. If you're going to do bullet points, if you want to hit the QWC, you need to ensure that you're doing good quality sentences. I would get all 4 marks for doing it and delivering it just like that. You do not need to do it in continuous prose. Next question. Moving on nice and quick. Okay. Oh, it's a weird setup. Methanol and ethanol, propanol, butanol are alcohols. They are all liquids that evaporate easily when warmed. Okay, student uses the apparatus to compare the times for the 4 liquids to evaporate. Oh, interesting. So we've got hot water, we've got the alcohol, so we're going to have the water vapor is going to come up here, and the water vapor is going to hit that, and it's going to be heating up the ethanol there, and it's going to then cause the ethanol to get warm, and itself is going to evaporate. Okay, it then says she uses the above method. Pour some methanol into terrible chemistry. Pour some methanol into evaporating. Place the evaporating station on top of a beaker containing hot water. Well, the question is, how hot is that water? So that's a random thing to say. It's not random, sorry. It's just unclear. Measure the time taken for the methanol to evaporate completely. Repeat the experiment using the different alcohols. State 2 variables that the student should control. Okay, so top answers is going to be the volume. Please note that I'm not using mass here. The volume of alcohol. If we're going to compare these liquids, I need to make sure that we're using a fixed volume. So 5 centimeters cubed would be a good choice, perhaps. We don't want to be putting a huge amount of it into the atmosphere. It's not ideal, especially when the gas itself is flammable. Alcohols burn really well. So putting that, which by the way, actually explains why they're doing it over hot water, seems very reasonable. The next thing, of course, is the temperature of the water. Well, it's very clear that she's not done that particularly well. So it's going to need to make sure the temperature of the water, is the same. So very reasonable. Can I just also say that I would probably want to say the volume of the water too, although in reality, I don't think it would probably actually make much of a difference. It could do, but what you tend to find is that because it's the vapor traveling up and hitting the bottom of the vessel, like even though if you had a water volume which was down here, it would cool down much quicker, which means I don't think it would be a particularly fair test. But so my third one there would be the volume of water in the beaker, but it's very obvious what they're asking for here. I do feel like I want to check a mark scheme at that point. It's the first one so far that I really want to see a mark scheme. Yeah, okay. Let's have a look at a mark scheme. I do have the mark scheme. I just haven't looked at it yet. I always prefer to do these under exam conditions. It's good a practice for me as anybody else. Gray. Oh, allow black. Isn't that nice? Thanks, EdXL. That's very kind of you. They will allow black. I like it. Fab. Oh, isn't that fascinating? Can you do it all in one go? You'll be able to do that all in one go. That's all right. Potassium, add chlorine, water. Allow, mix the two solutions. I'm in the allow box. Still not great. Add the two together. All right. Solution turns orange. It says allow any combination of orange, yellow, or brown. Wow, they're being very generous. Good old LXL. Bromine displaces. I like it. Bromine is displaced. Therefore, chlorine is more reactive. That's nice to see that. But it also, I am recognizing here that, you know, I'm in the accept column for mix the two solutions. That's not an ideal place to be. I do think that's a bit ridiculous. They're doing that for clarification for people who mark the papers. Oh, the two variables. Right, the volume of liquid alcohol used and the temperature of the water. Top answers. Allow amount of liquid alcohol. Ugh, I hate that. Ugh, that's horrible. Ignore mass, ignore volume. Oh, ignore volume of water. Okay. I'm not particularly in agreement with that, but all right. Statewide, it's not safe to heat the evaporating basin directly. Alcohols are flammable. Alcohols are flammable. And you're heating them to produce a gas. That is not a sensible thing to do under any... That's a bit like saying, do you know what? I'm just going to heat up petrol. You know, it's not a good idea. Next. 4 alcohols, methanol, ethanol, propanol, butanol. It's nice to see the organics making an appearance year 11. It's also nice to translate these into displayed diagrams. Can I just make an emphasis here? This bond here. There is a big habit for students to get rid of it. It's the internet's fault. The internet is full of great resources, but it's also full of terrible chemistry. The only bond that really matters in this molecule is that one. It's what makes it an alcohol. Please, please, please don't make it disappear. So we're going down, they're getting steadily bigger. And it says, first thing, calculate the mean time for the butanol to evaporate. Right, where's my data? Student A, oh, hang on a minute. 4 bits of data. Right, so yep, no, yep. It's always nice to go through and spot anomalies. That is clearly an anomaly. We're going to ignore that. So 64 plus 63 plus 60 divided by 3. We're working at an average. If they then, by the way, at this point, it's nice for me to just say, the question is, why repeat? Why repeat practicals, experiments? And the answer is number 1, to be able to spot anomalies. You can't spot an anomaly anomaly, spot anomalies, then to discard the anomalies, which is what I've just done, discard anom, and calculate a better average. Calculate better average. It's always good. AVG, nice. Okay, so add those together, 64 plus 63 plus 60, all divided by 3. And by the way, same thing again with the relative atomic mass. It's nice to have a rough idea in your head what you're aiming for. Well, it must be between 60 and 64. It's got to be an average. 63 is in the middle, so I've got more at the upper end. So we're going to be around about the high 62s, I'm assuming. 62.3. All right, 62.3. So if I got a number which was 197, then I'd be like, oh, that was ridiculous. How did I manage to get that? You guys do make calculator errors. Please don't think I'm having a go. I'm not. Under exam conditions, I would make it do because it is nerve-wracking. I get it. Explain how the results show that which of alcohol evaporates more easily. Right. Explain how the results show it and which alcohol evaporates most easily. So the first thing I think I'm going to do is answer the second point. Which one evaporated the most easily? And that's the mean time. So it's going to be methanol. So methanol evaporates most easily. And I'm going to state why, and that's because the number's the smallest. The mean time is smallest. I'm done. Check the mark scheme. Don't like the question? Check it. I'm also going to check all the others. Volume of liquid, we fixed that one. Alcohols, liquids, or flammable can catch fire easily. Allow 62.3. Explanation, methanol, because the time taken is the shortest. Oh, except because the lowest mean time. Oh, I said smallest. It's not great, is it? Don't like it. I'm going to make the amendment there to myself. I don't want to say, so it has, the mean time is the shortest. That's better, of course, short time. Yeah, I shouldn't say smallest, not great. State the relationship between the number of carbon atoms in the molecule and how easy it evaporates. Well, 1 carbon was 23 seconds. 2 carbons in a chain was 33 seconds. 3 carbons in a chain was 48 seconds. And 4 carbons in a chain is gone up to 62. So it's a pretty easy relationship. We're going to say, number 1, as the carbon chain gets longer, the mean time increases. Increase carbons, increase time. Check it. Always like to check all those practical ones. As the number of carbons increases, the ease of evaporation. Ooh. Ignore reference to time taken. First mistake from Mr. Duncan. That's why I check these things. So we're saying as the carbon chain gets longer, it is more easily evaporated. That's ridiculous. Stupid. Made my second error there. I probably would have given myself that one in terms of the smallest time. But I shouldn't do. It's better to make the correction. But as the carbon chain gets longer, the harder it is to evaporate, the less easily evaporated. Evap. Easy fix. No, that was not. Do you know what? And I should have got that. I definitely should have got it. Mean time, it already appeared there. To say mean time twice, yeah. So I definitely would have lost that mark there for sure. Next, this question is about metals and metallic bonding. Giant lattice of cations surrounded by a sea of delocalized electrons. So state which describes metallic bonding. Electrostatic attraction between oppositely charged ions. Nope, that's ionic. Just a reminder, in order to be able to test, if somebody said, I have an ionic solid, I think X solid, I think it's ionic. How do I find out? What you do is melt and see if it conducts electricity. Step 1, melt it. Step 2, see if liquid conducts electricity. E minus. Electrostatic attraction between the nucleus of the two atoms of a pair of electrons. Nope, that's covalent. Electrostatic attraction between positively charged and delocalized electrons. See, we're done. Electrostatic attraction between atoms? No, don't think so. Technically, it's a WIMP, that, but still. Aluminium is malleable and can be easily shaped to make saucepans used for cooking. State 2 other properties of aluminium that make it suitable for saucepans. Oh, well, number 1, it's a good conductor of heat. If you're going to heat something, it needs to be that. Good conductor of heat. What's the other one? It's lightweight. That's actually a really good one. In fact, aluminium's lightweight. And if you're going to hold a pan, lightweight. Lightweight. There's another one actually, that aluminium is a very special metal. Aluminium is incredibly, and they love picking on it. Aluminium is very high up on the reactivity series, just to quickly show you. So the reactivity series, it's high, which is really odd. Oh, I should have just gone for it. Reactivity series. Aluminium's surprisingly high. It is higher. It's higher than carbon, not quite as high as magnesium, but it's pretty high. And magnesium, you guys know, burns with a bright white flame. It's a very reactive metal. Aluminium's just below it. This is a reactive metal, yet we can put it on a Bunsen burner flame. I don't think we want to make a frying pan out of magnesium. Bad plan. And the reason why is because aluminium forms a protective oxide layer. It's a fascinating element. And the reason why this is so lucky, it forms a protective coating of aluminium oxide. And aluminium oxide is unreactive and insoluble, which means it seals it. So you form a protective layer of aluminium oxide, Al2O3, which seals it. And what that means is it's incredibly corrosion resistant. So do you know what? The annoying thing is I'm only allowed 2. I'm actually going to go for my original 2 since I've done it. That's going to be a top one for sure. It's whether or not they give me the lightweight. Let's check the mark scheme. High melting point, of course. Okay. Yeah, reasonable. Okay, so we did hit it. M5, allow any 2. Does not react with food or affect flavor. Ha! Resistance to corrosion, fair enough. High melting point, low density, lightweight, and strong. I spelled weight wrong. I'm an idiot. Oh, my bad. I did know it. I did pause when it did it, and I was like, oh, stuff that up. There we go. So, and by the way, it's nice to talk about as to why aluminium actually forms that layer instantaneously. When you actually produce it during electrolysis, as soon as it's exposed to air, it forms the protective layer, it seals it. Next. Okay, on to alloys. Oh, magnalium. That's such a cool name. I do like that, magnalium. It does sound like a superhero, doesn't it? I totally agree. Magnalium is an alloy of aluminium and magnesium. The diagram shows how the atoms are arranged in this alloy. Right, now, it's nice at this point just to mention malleability. Malleability and stroke ductile. So just to explain, a malleability is the ability to be reshaped when solid without breaking. I know. Can be reshaped when solid without breaking. That's malleable, without breaking. The next one is ductile, can be stretched into wires. And do you know what? Every time ductile comes up in a GCSE exam, the students always flounder. I think it's just, I don't know whether or not it doesn't come up very often in papers, but every time it doesn't, maybe it's just because I'm remembering it appearing every 5 years or so and students panic. You don't need to. The reason why I put these two together is because their explanation is the same. And their explanation is that in a metal, the atoms are arranged in rather beautiful layers. And those layers have the ability to slide. So I can now move that layer and form it one atom over. So 2 marks, well organized layers, and those layers can slide. can slide when struck, if you like. Next, state what is meant by the term an alloy. A mixture of metals. Now, can I just point out, I actually don't like that definition. The mark is going to be for mixture. They're probably going to give it to me. But if you look at steel, the most common asked alloy at GCSE is steel. Steel, we know that iron is Fe, and pure iron, all the atoms are the same size. Here's a picture of iron with the, this is the rudimentary year 9 image. This is year 9 chemistry. And this explains the malleability and ductility of metals. And then you have steel. Steel is a mixture of iron mixed with carbon. And what that means is you then get the smaller carbon atoms interfering with the layers. And which means those layers can no longer slide so well. So these are the carbon atoms. And it's all to do with the sizes. So the layers have become disrupted. But the reason why I mention this is also because that is a metal and a non-metal. So it'd be nice to see what they wanted at this point. A mixture of 2 or more elements, one of which is a metal, except a mixture of 2 or more metals. Fab! I got it on except. I don't really like it. Theirs is better. A mixture of 2 or more elements, one of which is a metal. It's a bit clunky. I kind of like just giving mine. It seemed an awful lot easier. But I do understand that. A mixture of metals. Oh, I think you needed 2. Yeah, a mixture of 2 or more metals. Of 2 or more. I will make that adaptation. 2 or more metals. And I can actually put, if I like, 2 or more elements, one being a metal. Explain why magnesium is harder than aluminium. So, number 1, atoms in magnesium, atoms in magnesium have different sizes, I've just done something super important there. Guys, do you see these boundaries? If you're writing and you go over that line, that will be cut off. These papers are scanned by computers, and if you write in the margin, they will not mark it. I warn you, make sure you keep everything on the lines. Atoms in magnesium have different, I'm going to compact it, have different sizes. Layers are disrupted. Layers are disrupted. Cannot slide as easily. Compared to aluminium, to Al. Aluminium has all the same size atoms, so therefore the layers are in order. Next, during the Second World War, engineers developed a rocket-powered aircraft. Hydrogen peroxide tank, hydrazine, holy mackerel, hydrazine and a combustion chamber. Wowzer. That's a bit scary, that. Those 2 chemicals are terrifying on their own, let alone together. The aircraft carried these 2 liquids. When the 2 liquids mix in the combustion chamber, they evaporate and they rapidly form nitrogen gas and steam. The reaction is exothermic. Wow, true rocket plane. What that meant is when you ran out of fuel, you just glide back. It's a bit scary. You'd also imagine those things exploding. It's not really a good idea in terms of the chemistry-wise. The equation is below, and they've drawn out all the molecules. Wow, they have been so generous. Folks, I haven't seen them do that in 5 years, maybe longer. They never do that. They're being super nice to you. Tell you what, they ain't going to do that yet. They ain't going to do that next year. That reduces the difficulty of the paper significantly. Right. It then gives us all the bond data. Use the data in the table to calculate the total. So, by the way, folks, this question is bond enthalpy, and the equation is burp, which is bond data. The equation is reactants minus products. Right. So we need to smash all the bonds. So we're going to smash all of these. So we've got the total energy required to break all the bonds of the reactants, right? Here's hydrazine, and here's hydrogen peroxide. That's hydrogen peroxide. How many of them were there? Two hydrogen peroxides. I'll draw those out because it actually makes it a little bit easier. Right, let's look at our bonds. So first of all, I have got nitrogen and hydrogen bonds, and I have 4 of them. Where's that guy? I'll highlight that in yellow. Right, so I have got 391 times 4. I'm going to add that to, going to color code this, NN, and I've got 1 of those. Add 159, add, orange, oxygen hydrogen bonds. Got 4 of those, plus 4 times oxygen hydrogen. Do that there. Oxygen and hydrogen. 4 times 463, and then I'm going to add that to last one, oxygen bonds. So there's that guy. So I've got plus 143 times 2. Right, add those all together. Got my calculator in front of me. Brackets 391 times 4, close brackets, plus 159 plus open brackets 4 times 463, close brackets, plus open brackets 143 times 2. Enter. Total energy 3861. I like it. Next, use the data to calculate the total energy released when the new bonds are made. Right, so we're going to form nitrogen gas, a triple bond, and we're going to form water. We're going to form steam. Right, how many of each one did I make? I made 1 and 4. Okie dokie. So I made 1, and I'm going to put times 4 there. Right, because it makes it easier. So I'm going to do, once again, yellow bond. So this is a nitrogen-nitrogen bond, and that's over here. Highlights didn't work there. There we go. And that's, wow, 9. I'm going to go 945 times 1. I know I don't really need that. It's just, I felt like I should have done it up there. And then, this one is, all I have got is oxygen and hydrogen bonds. But now I have 2 per molecule. And this is much more likely of what you're going to get in an exam. Times that by 4. The total number is 8. So 8 times OH bonds at 463. Right, add it up. 945 plus open brackets, 8 times 463, close brackets. I get 4,649. Right, calculate the enthalpy change. This is where Bert comes in. Reactants minus products. So the reactants, so my total equation is going to be 3861 minus 4649. So 3861 minus 4649. Go. And I get minus 788. And we're done. I like it. Include the sign. The marks there are for that equation, that sign, and that number. 3 marks. Move on. I like it. Explain in terms of bonds broken and bonds made while the reaction is exothermic. Right? The energy absorbed by breaking bonds is less than the energy released when new bonds made. We're done. Right, draw a reaction profile. This was exothermic. So first thing is we have the start of the reaction and we have the end of the reaction. And this was exothermic. Note, it was minus. That sign means I am losing heat. That is exothermic, to lose heat energy to its surroundings. So I'm going to go start up here, and I need to put the people on it. So I have got my reactants, which was hydrazine and hydrogen peroxide. Let's balance it. There were 2 of those. And I'm going to end lower down being nitrogen gas and 4 H2Os. There we go. Exothermic. It's nice to do a bit more detail on this graph. So if they ask you about the difference between those two there, that is the overall heat change. This is the enthalpy change. That there is overall heat energy change, otherwise known as enthalpy. The enthalpy change, delta H. Right, so this arrow here, that arrow there, that one is the activation energy, or, and I emphasize this, or the energy needed to break the original bonds, needed to break ORI bonds, original bonds. Yeah, and this one, this last arrow, the total height of that one, that there is the energy released when the new bonds are made. Energy released, new bonds made. And you can see that the energy to break the original bonds is less than the energy released when the new bonds are made, hence it being exothermic. Next, how are we doing that? Scroll up. Next, name the substance. So some cars from Brazil use ethanol as a fuel instead of petrol. Oh, okay. The ethanol is made by fermentation of glucose, which is obtained from sugarcane. The sugar is extracted from the sugarcane and then dissolved in water to make a sugar solution. Name the substance that is added to the sugar solution that causes it to ferment, and that is yeast. Catalyst for this reaction. Catalyst, that's yeast. What temperature is most suitable? Body temperature. Yeast is living. We don't want to freeze it, and we definitely don't want to cook it. Not a great plan. Explain why fermentation is done in the absence of air. Right, the reason for that is because yeast, if you don't do it anaerobically, the yeast will just turn the ethanol into CO2 and water. They'll do aerobic respiration exactly the same as what you do. So if you do in air, you get C6H12O6 plus O2, and the yeast will just do aerobic respiration and produce CO2 and water. 6 of those and 6 of those and 6 of those, all 6s. So that's aerobic, and we don't want that. There's no ethanol here. Anaerobic, anair, we get C6H12O6 going straight to CH3, CH2OH, and CO2, and you get 2 of those and 2 of those. There we go. So what you want to say is, for 2 marks, why it's done in the absence of air, bullet point number 1, with air present, no ethanol will be produced. No ethanol produced, because aerobic will take place. No ethanol produced. Only carbon dioxide would be produced. Do you know what? I wonder where the second mark is. Oh, go back, mark all the rest. Regular arrangements of atoms. Because magnesium atoms are larger than aluminium atoms, allow layers can't slide, and therefore it's more difficult for layers to slide over each other. Next, bonds broken, bonds made. Right, what's the total answer? I want to know the answer. What was the number? There. -788 is what we got. More energy is given out when the bonds are made than is taken in when the bonds are broken. I like it. There's our graph. I like it. Ignore horizontal axis. All right. Start and end always goes on it. Yeast, 30. Right. Explanation of either of the following pairs. M1, oxygen in air would react with the ethanol. Or the fermentation, ethanol would not be formed. Blimmin' heck. I got that right at the end. M2. If fermentation, respiration needs to be anaerobic. So I would have got it if I'd written down the fact that it would have gone aerobic. Right, that's very interesting. The oxygen in the air would have reacted with the ethanol to form ethanoic acid. Yeah, okay. By the way, that's garbage. That's not true. That is genuinely incorrect chemistry. Because if you leave a fermenter open, you won't get ethanol at all. You just won't. It's garbage, rubbish. So in air, no ethanol produced because aerobic respiration would take place and you'd produce CO2 and water only. That's what I would write. State what is meant by the term fuel. Ooh, a substance that when burnt releases heat energy. I like it. Next, write a chemical equation for the complete combustion of ethanol. Right, complete combustion means CO2 and water only. So ethanol, CH3, CH2OH plus O2 goes to complete combustion, gives me CO2 and water. By the way, carbon dioxide, of course, is glow. If they ask for the problem with it, why do scientists have a problem with carbon dioxide? It is global warming. And by the way, oh my goodness, global warming. Oh, poor Australia. Hats off to Australia. I donated recently, by the way. But if it was incomplete combustion, it's nice just to switch over, do those extensions. If I had incomplete combustion, then I wouldn't get CO2 and water. I'd get carbon monoxide and water. And that one is toxic, prevents oxygen from being carried in the blood. Or even less oxygen. I can balance the equation to show you if you like. Even less oxygen and you'll get carbon particulates and water. And carbon particulates cause global dimming. So all the problems with incomplete, but there are problems with complete also. But complete also gives us the most amount of energy. So balance the equation, of course. You can't leave an equation unbalanced. 2 carbons, 6 hydrogens. Ooh, not very nice. Ooh. Yeah, it's going to be a fraction. All right, fine. 4 oxygens, 7, 3.5. And then double them all. Double it, 2, 7, 4, 6. Yeah, just watch out for that. I think they're probably, I'll show what. Ooh, did they allow the half? Did they allow the half? Have I just stuffed something up there, guys? They've made a mistake. Oh, I made a mistake. Oh, I lost another one. I've done a classic mistake. I've literally fallen into my trap. Do you know what? I talk to my kids so much about this, and it's such an easy mistake to make. There was already a carbon in the ethanol. Definitely would have lost that in an exam. Don't rush. Take your time. Count your atoms. 2. Yeah, I should have counted it. Yeah, so we have got 7, but there's 1 already there. I only need 3 to give me the 6. Oof, watch out for that, please, year 11. Next, ethanol is manufactured from steam and ethene. The state the conditions required. This is direct hydration. And the conditions, temperature is 300 degrees Celsius. And the pressure is 60 atmospheres, 60 atm. You can't have any higher because the ethene would polymerize. So you can't go up any higher than that, even though it's in equilibrium and it favors the right-hand side at higher pressure. The catalyst, by the way, is concentrated phosphoric acid. Catalyst, they do actually ask that as well. Catalyst is concentrated H3PO4, phosphoric acid. The ethanol is heated with acidified potassium dichromate. This is the oxidation of alcohols. State the color. The color change of potassium during the reaction from orange. By the way, a beautiful orange as well. One of my favorites. It's like highlighter orange. Beautiful. And it turns green. If you leave it long enough, it turns blue. Oh, do they allow blue? I'd love them to allow blue. I'd love them to. Orange to green. Oh, they don't allow blue. Orange to green is the right answer. It's just if you leave it long enough, it'll go to blue eventually because you form chromium 2+. The structural formula of ethanoic acid is this. Draw the displayed. Always nice. Thank you very much. Draw your bonds. Guys, don't forget that bond. Yeah, displayed formula. A drawing showing all bonds within a compound. Most common mistake is to students to do that because they've seen it on the internet. Do not do it. All bonds must be shown. Right, write an equation for ethanoic acid and sodium. So I'm going to form CH3COONA and hydrogen gas and balance it. One ethanoic, one sodium. The hydrogens, right, we need two hydrogens because we've lost a hydrogen and we've got two there, so we need two of those. Therefore, we're going to need two of those. Therefore, we're going to need two of those, and we're done. Yay, we're done. But I wonder if they would allow a fraction. Did they allow a fraction? They allowed a fraction. Yeah, allow multiple. Oh, yeah, they allowed a fraction. Wow. Oh, ignore. Look, ignore. Yeah, score. Oh, yeah, so they do give it to you. Oh, that's annoying. I don't know. Maybe not. I never know. Next, dinitrogen tetroxide is a colorless gas. The nitrogen dioxide is a brown gas. The two gases can exist together in a dynamic equilibrium. Explain what is meant by the term dynamic equilibrium. A chemical reaction in which both forward and backward reactions both forward and backward reactions are occurring at the same time. Their rate I've got a real problem. Their rates are equal. Their rates are the same. Their rates are the same. And the concentration of reactants and products and prods remain constant. Next, 3 marks, but only 2. Their rates are the same. I like it. Okay, this equilibrium mixture is brown. Okay, sealed in a tube, allowed to reach equilibrium. The pressure of the gas syringe is increased by pushing the piston. The mixture is then allowed to reach equilibrium at the same temperature. Explain why the new equilibrium contains less NO2 than the original mixture. Right, this is equilibrium, and we are going to run COFs. So COF stands for knowledge, and that knowledge comes from the equation. Knowledge from equation. Next, oppose. Most commonly lost mark at GCSE and A level. Favor and shift. 4 marks. You've got to go the whole hog here, folks. Knowledge. So this is pressure. And in pressure, you have to consider molecules. So if you find the equation, which they've probably given us, which is there is 1 molecule on that side and 2 molecules on that side. Right. So knowledge. There are 2 molecules or moles, other one. There are 2 molecules on the left, 1 on right. Yes, I've got into the margin, but I'm allowed. There are 2 molecules on the left, 1 on the right. First of all, I need to go to the equation and tell them what I see. Next, oppose. So hang on a minute. They squashed the syringe. If you squash the syringe, if you have a balloon and you were to squash it, you're going to be putting the balloon under more pressure. And that balloon's not going to like it. We're raising pressure. So oppose. We increased pressure. That's actually harder because they didn't say it. They just said push the plunger. They haven't mentioned anything to do with pressure. It's slightly more tricky. We increased pressure. Equilibrium. The opposed thing's really tricky because you have to state the whole thing. You have to say what we have done and what the equilibrium will then try and do, which is always the opposite. We increase pressure. Equilibrium will reduce pressure. How will it do that? By favoring what? By favoring less gas, less molecules of gas. And which way is it going to go? It's going to shift from right to left. Shift right to left. And I'm then going to go more N2O4 than NO2. Is that what they actually said? Explain why the mixture contains less NO2. Yeah, fine. Next. A student suggests that the new equilibrium mixture would be lighter in color than the original mixture, as there is now less NO2. State why the new equilibrium position is actually darker. Huh. Well, the answer is it shouldn't be. I can tell you why, and that's because you've raised the concentration of the NO2 because it's in a smaller space. That's actually a really, really mean question. We know that the equilibrium is going to go there, going to go in that direction. It's going to shift that way. And it's going to become more colorless than brown. However, the reaction happens in 2 stages. And by the way, you can look these up on YouTube. There's some great videos out there for this particular equilibrium. And the reason being is because if you start with your syringe and the plungers there, and this is this brown like this. Let's try that again. I'll seal it. And it's this kind of brown. When I squash the syringe, when I take that syringe and I push it in, let's cap it again, and I push it down to here, all of a sudden, I'm going to take all of this brown gas and push it into a smaller area. So I need more colors, and it will get darker like that. But then what will happen is it will shift. The equilibrium will then have time to adjust, and it will get lighter again. So you actually get to see this rather bizarre kind of roller coaster ride of colors. And what they're saying is the fact that it's actually going to be darker because the leftover NO2 is occupying occupying a much smaller space, and therefore will it be at a higher concentration than the original. God, what a faff! The equilibrium hasn't become established yet. Oh, both taking place at equal rates. The position of equilibrium has moved to the left, right to left, all of that. Because there are fewer moles on the left, concentration of NO2 has increased. The concentration of NO2, there's the answer, 0.2. Yeah. So they're saying that the NO2 left over here, even though the equilibrium shifts back, because if there were 10 particles of NO2 in that space, and even if there are only 6 particles of NO2 in that space, that space is less than half of what that was, so the concentration is going to be higher. Oh, what a nightmare. So they just wanted you to say the concentration of NO2 will have increased. What a horrible, I wouldn't have got that in an exam. No way would I got that. That's a horrible question. That's evil. They're looking to trip you up. It's not very nice. Carbon monoxide and oxides of nitrogen are produced in the car engine. Burned in petrol, the oxides are removed by a catalytic converter. State how oxide of nitrogen are produced in a car engine. So the nitrogen comes from the atmosphere. That comes from the air. That air is sucked into the engine and reacts with the oxygen that was in the air at high temperatures at the spark plug, and it forms NO2. Balance the equation. There we go. That works out. So you need high temperatures. High temps. At high temp, what I would write in the exam, at high temperatures, the N2 from the air reacts with the O2 from the air to form NO2. You're done. Give an advantage of allowing oxides of nitrogen to escape the atmosphere. By the way, my laptop has stopped. Oh, it's crashed. That's back. I didn't read the question. RTFQ, read the full question. Give a disadvantage of allowing, it causes acid rain. Oh, idiot. It causes, I won't put it. Don't like it. Very scientific. NO2 causes acid rain. Just like SO2. SO2, by the way, just put SO2 also does this as well, but that's the answer for this particular question. Write a chemical equation for the reaction between nitrogen monoxide and carbon monoxide to form CO2 and nitrogen gas. NO plus CO goes to CO2 plus N2. It ends in gen. If it ends in gen or ene, it is in a pair. And balance. One nitrogen, two nitrogens, by oxygens. Ugh. 3 oxygens on this side, but then 2, I'm going to double that. That makes 4, and then double that, and it works. There we go. Next. Okay, explain a safety precaution when doing this experiment. The concentration of sodium chlorate in bleach. Bleach. Okay. Bleach is reacted with hydrochloric acid. The excess hydrochloric acid is added to the bleach. Explain the safety precaution that be taken during the experiment. Well, A, you've got HCl is corrosive. HCl is corrosive. By the way, it's asked for a precaution. The precaution is gloves and goggles, but gloves is the top answer. HCl is corrosive, therefore can burn skin. That's the hazard. Hang on a minute. Yeah. So that's the hazard. Hazard. That's the risk. No. Risk is hazard. I've forgotten. I can't remember. Mind gone blank. Burn skin, and the precaution is wear gloves. Wear gloves and goggles. Obviously. Ovs. You're also using bleach. It's also corrosive as well. Very nice. Calculate the amount of moles in the chlorine gas produced. Assume 1 mole of chlorine gas occupies this space. Right. Ooh, lovely calculation. So in excess of dilute hydrochloric acid is added to 4 centimeters cubed of bleach. 60 centimeters cubed of chlorine gas is produced. Right. Number of moles is V over 24,000 because I'm in centimeters cubed. So 60 over 24,000. How easy is that? Oh, that's a bit of a gift. So 2.5 times 10 to the minus 3 moles. 10 to the minus 3 moles. Next, determine the amount of moles in the chlorate. Right, look at the ratio from chlorine. We've just worked out the moles of him. The ratio is a 1:1 to the chlorate because there's an invisible one there and an invisible one there. So it's a 1:1. So the moles is the same. So the moles is 2.5 times 10 to the minus 3. Calculate the concentration. I'm also going to put 1:1 ratio there, even though it's only worth 1 mark. Calculate the concentration of moles per D included with the solution. Number of moles equals C times V over 1,000. The concentration is what I am after. Let's reorganize. Moles times 1,000. Bring the 1,000 up. Bring the V down. Times 1,000 over the volume, which was 4 centimeters cubed. Number of moles. 2.5 times 10 to the minus 3 times 1,000. The 10 to the minus 3 disappears, by the way. That's pretty easy. And then it's 2.5 over 4. That's not too bad, is it? So times 1,000 and then divided by 4. So the concentration is 0.625 moles per dm cubed. I think we have come to the end of our paper. Wow, smashed it. And we have been going for 63 minutes. Fantastic. Right, guys, let's see if I can bring you back. See if I can bring you back, folks. Let's go to here. Let's bring it all back. Bring it back. See if we can do that. Yay, we're there. Right, guys, thanks so much for coming along. I hope it was useful for you. If you've got any questions, I'm happy to do another paper 1 and paper 2. Obviously, I'd like to do as many as possible before your actual real exam. But I hope you found this useful today, ready for your mock exam. So, guys, have a nice rest of your evening, and I'll see you all very soon. Take care, guys. All right, bye.